Hello everyone. Today we are starting rotational motion, and that is chapter 10. We did skip some of the stuff from chapter 9 because after chapter 10 and 11, things are going to get more complicated, and we're going to even combine the motions that we've seen so far. So we will need more time to really absorb the material, and especially since it's online now, I feel like we need even more time. So the next exam, which is next Friday, it doesn't include the rotational stuff yet. Okay, so I'm really just giving you more time to like really absorb the material. But if you the homework is also from chapter 9. It's also due that day, and I would definitely and strongly suggest that you finish the homework this weekend, so that you have more time to study for the exam and also ask questions, and then also like the kind of again study the new chapters, which are very important for your engineering career. Okay, so let's start with rotational motion then. So we will expand our methods further to facilitate the analysis of rotating objects. And we will repeat for rotating objects everything we've done in this class for translating objects. So we have now translational motion. That's what we learned in chapter 2 and 4. In terms of motion. In chapter 5 and 6, we looked at the Newton's laws. In chapter 7 and 8, we looked at the conservation of energy. In chapter 9, we looked at momentum. Okay, so now we're going to apply these to rotating objects, and we will talk about rotational motion. And later, we will combine those two motions. So our goal is to develop an understanding of the behavior of rotating objects, since many practical devices contain rotating objects like gears, wheels, pulleys, motors, and you are probably going to work with them when in the future, and even in the future classes. But I'm also thinking about when you get a real job and such. And so we will consider two basic types of rotational motion. The first one is rigid body rotation. So this is also, again, this is a pure rotational motion. Okay, only the rigid body rotates. It doesn't move in a translating way or linearly. So rigid body rotation is a rigid object rotates about a fixed axis. Examples are gear on a fixed motor shaft or flywheel, and a rigid body does not deform or change its shape. Okay. Change shape as it rotates. Like, remember the water balloon that we were throwing in air, and then it deformed, and it changes its shape. So that's not a rigid body rotation. And after that, so we are going to talk about combined motion. What do we combine? We combine this rigid body rotation, rotational motion, and the translational motion, as we learned earlier in this class. What are the examples? Like a wheel on a moving car. We've been ignoring the wheel motion most of the time because we didn't know how to deal with them. So we are going to learn about those now. Or ball kicked across the ground, axe thrown at a target, yo-yo, and you name it. So let's focus on the rigid body rotation first. And so we're going to talk about kinematics of rotational motion. Again, we are not really, this is a different topic, but we are going to use a lot of what we learn, and it's very important and it's very crucial that you remember those and you recall when they're needed. This topic will build upon what we learned before. So you'll follow a similar approach to how we describe translational motion, and by specifying the position, location, and velocity and acceleration. Those were the descriptors of the motion. There still are. Okay, so instead of just labeling them like that, we're just gonna add angular, the word angular before them to make it for rotational, and we'll see how else we're gonna change things. So again, instead of saying position, we're saying angular position for rotational motion. but it's very similar definition, okay? To specify the position of a rotating object, we put a reference line. So you can see the dashed line here. I'm going to highlight a few things while I'm doing this. So here the reference line. Since now things are three-dimensional and rotating, it's going to be a little bit harder to imagine things. So again, if you have any questions on these, you can email me if this something is not clear in the class notes. I'll try to also highlight some things when I'm explaining things on the videos. Okay, so we put a reference line on the object and specify its angle. So you can see that the angle is with the x-axis and to the reference line. This point is also important. The origin is the rotation axis, and this solid irregular shaped object is our rigid body. Okay, and we are rotating it from that rotation axis at the origin, and we are just kind of choosing this point here and then drawing a reference line, the dashed line, and when you rotate it, you create that angle theta. Okay, and doing so, rotating will completely specify the object's position or orientation. Okay, so a couple of things in here. Since now we have rotational motion, we need to understand rotational parameters. S here is the arc length. Okay, so you can see that when you move that object, this is not a straight line, it's like an arc, and R, the reference line R, is like the radius. Okay, because your rotation axis is fixed, R is fixed, and when you rotate that, it creates an arc length. So S, if you come here now, S is the arc length traced out by the reference line, and R is the length or the radius of the reference line. Okay, so from the geometry, we can write the angle in terms of arc length and the radius. Okay, and so theta is going to be our angular position. So when we say position in rotational motion, you don't recall x, y, you recall theta. Okay, theta is the position, and that is in the form of arc length divided by the radius. And one important thing here is the unit is radians. There are several other units that you can use, and it will be given. If it is not radians, that means you need to do a conversion. And so the radian is the one that has no unit or no dimensions. So if you have, for example, just gonna jump to this part. This is the conversion factor between radians. 2 pi radians is equal to 360 degrees, 2 radians to degrees, and also degrees to, or radians and degrees to revolution. Okay, and because of this conversion factor, like you can, if the degrees or revolution is given, then you need to convert it to radians. So this is what you need to use. But the only unitless or the dimensionless one is the radian. So that's what we need to use. So if you look at theta in units, so it is radians, and we show it with RAD. And that's equal to arc length. Arc length is a linear length, so we're going to use meters, okay, and divided by radius. Radius is also linear length, so we're going to use another meters. So what you're getting is there's no unit here, right? So they cancel out. So radians is unitless, but degrees and revolution is not. So you have to make sure that when you're calculating angular position, you convert whatever is given, if it's degrees or revolution. If it's not in radians, then you need to convert it to radians. Okay, so in a complete circle, when you make a full circle, full turn, then the angle that you will cover is either 2 pi radians, right? So you're starting from x and then you're coming back to x. What is this angle? It is 360 degrees or 2 pi radians or 1 revolution, right? It's just 1 turn. And as an object continues to rotate, theta continues to grow. As you go over and then draw that circle again, theta increases as the object rotates, because theta means that's from the reference line, right? So that's gonna increase. So after rotating through 2 revolutions, theta will be twice as much as 2 pi, so it's 4 pi. And knowing theta at any time will tell you exactly how the object is oriented, okay? And its theta is its position, so that's, you're finding its position that way. Similar wording, displacement. Remember displacement? It was the change in position, right? Now we're going to call it an angular displacement. That means it is going to be the difference, the change in theta. In this case, instead of x or y, we have theta now. So delta theta is the angular displacement then, and that will be theta 2 minus theta 1. So in the linear motion we had, for example, delta x. So what was delta x? That was x2 minus x1. In three-dimensional motion we had delta r. That was r2 minus r1. Still similar. Now our displacement is theta because it's angular displacement. So initially you had this theta 1 and then you moved even more, and that is your theta 2. Okay, and that's the disk is your object in this example.